I want to begin by filling something in that happened during the recorded lecture last Friday, but let's just get it up into this set of notes for posterity. So, some of the things that happened during that particular day were computations of trig functions at some particular reference angles, namely the angles of pi over 4, pi over 6, and pi over 3. And let's just go ahead and state them. So at an angle of pi over 4, cosine is root 2 over 2, sine is root 2 over 2. Right, if you like, that's like a 45-degree angle, so that should have slope 1. So the x and y coordinates should be the same. And that's the only thing it could be, because x squared plus y squared needs to be 1. At an angle of pi over 6, an analysis of a particular right triangle tells you that you should have cosine equal to root 3 over 2, sine equal to 1 over 2, and the opposite at pi over 3. So hold on to that for now. Let's recall the identities that we've developed so far last time. We computed sine and cosine at certain shifted angles. I think that's as not in the way as I can get the screen to be. So let's go ahead and compute them. If you take an angle and add 2 pi k to it, what does that do to cosine? Stays the same. It is still cosine. What happens if you take an angle and make it negative or subtract it from 2 pi? Right here it stays the same. And perhaps here's a good way to see that. You can go up by pi over 6. Or you can go down by pi over 6. Either way, you're making the y values negative, but the x values are staying the same. So let's do this. So here's an angle of 11 pi over 6, also known as 2 pi minus pi over 6. What should the resulting cosine be? Should be the same as for cosine of pi over 6, which, well, I guess is right here. It's root 3 over 2. Let's go over to sine and fill in the same two rows. Does adding 2 pi k do anything to sine? It does not. So when you make an angle negative, what does that do to sine? Gives me negative sine theta. So that means some things. That means if you, instead of rotating up by pi over 6, rotate down by pi over 6, you'll have the same y value, just negative. Negative 1/2. Could we do the same to get the other two angles in this quadrant? Yeah. It looks like sine and cosine at 7 pi over 4 will be the same as this, but the y value will be negative. Root 2 over 2, negative root 2 over 2. Same for 5 pi over 3 versus pi over 3. 1 over 2, negative root 3 over 2. Feel pretty good? And notice, that's really taking advantage of the fact that this transformation gives you a reflection over the y-axis. Making an angle negative just reflects things over the y-axis. So let's carry on with the other things that we did. What does replacing an angle by pi minus theta do to cosine? Right here it makes it negative, but that sounded like it had a question mark at the end. Do I have a second for it becomes negative? Cool. Yeah, it's negative cosine theta. How about sine of pi minus theta? Stays the same. So let's maybe draw some arrows indicating what transformation is being used. This gives you reflection over x-axis. Let's think about what transformation that gives.
Reflection over y.
Nice. Right. So instead of going up by just theta, you can go over by pi and then back by theta, and that would accomplish that. So I guess that tells you some things. So let's see. If you go forward by pi and back by pi over 6, you get an angle of 5 pi over 6. So what should the trig functions at 5 pi over 6 be? I hear a negative root 3 over 2. And how about cosine? Nope, how about sine? That would just be 1/2. It should be this point, but reflected over the y-axis, because that's what replacing an angle by pi minus that angle does. How about the remaining entries in that quadrant? Are those now equally easy to fill in? Yeah. 3 pi over 4. That gives you the point.
Negative 2 root 2 over 2.
I guess this last one is equally easy. Cool. That feel pretty all right? The other transformation, which I think we got to last time, was what happens when you add pi to an angle. What's the cosine of pi plus an angle? I hear a negative cosine theta, but again, you said it with not a whole lot of confidence.
Negative cosine theta.
That's better. Be confident when you are confident. Yeah, that's correct. How about sine?
Negative sine theta.
Negative sine theta. They both become negative because what transformation gives you that adjustment in angles? Reflect through the origin. Cool. So that means all of these points should be the same as these points, with x and y both negative. Nice. Let's do that. So cosine and sine of 7 pi over 6, right, that should be pi plus an extra pi over 6, should be the same as this point, but they're both negative now? Oh, it was, sorry. So every time I start, I have to hit a button that says autofocus lock. Otherwise, whenever I put my hand on there, it'll focus on my hand. It took me a significant chunk of the fall semester that this device was in here to figure out what on earth was happening. It was really stressful. Anyway, so all of the entries in that third quadrant should be the same as the entries in quadrant 1, just both negative. So let's do 7 pi over 6. What should sine and cosine at 7 pi over 6 be? Five pi over 4? Excellent. 4 pi over 3.
Negative 4 1/2. Negative root 3 over 2.
Cool. Nice. So here's how you can now use this diagram or a diagram like it. This tells you for what a bunch of trig functions are at some points. Now, while you could internalize all those values, I think you'll wind up automatically internalizing those values if you just keep on having to reference this diagram. And so this is something that I might encourage you have on things like note sheets for exams and stuff. Groovy. So let's now go back to the actual section and think about these remaining transformations. And nothing fancy will happen to get those. Oh, in fact, I see one of them we already did. cosine of pi over 2 minus theta. What's that equal to? I guess it's say again?
Sine.
It becomes sine. Sine of pi over 2 minus theta. I guess it is like right up there, so it's silly to ask. And that came from reflecting over the line y equals x. Right? So x, y coordinates should switch. Sine and cosine are x, y coordinates, so they should switch. Neato. That feel pretty okay? So there's one last transformation in the list. What happens when you add pi over 2 to an angle? And there are two reasonable ways to think of it. You can think of it geometrically by drawing some diagram in the unit circle, or you can do it algebraically by trying to realize that transformation in terms of transformations we've already done. And at a minimum, I'd like to do it algebraically, because that, I think, will be a useful example of combining previous ideas. So let's try to think in this language. I'd like to compute cosine of pi over 2 plus theta. And I don't know what happens when you add theta, when you add pi over 2 to an angle. But I know what happens when you do subtraction instead. Well, addition is basically subtraction. It's just subtraction by negative theta. So let's do that. Let's think about cosine of pi over 2 plus theta as pi over 2 minus theta. And so I'll play this game where I take the thing that I want to just ignore for now and I put it in a box. So cosine of pi over 2 plus theta is cosine of pi over 2 minus theta. I'll, in the short form, call minus theta box. Do I have a rule that tells me what cosine of pi over 2 minus box should be? Sine of a box, which I guess is minus theta. So cosine of pi over 2 minus a thing is sine of that thing. And the thing in the box is minus theta. Oh, wait, do I also have a rule that says what the sine of minus theta is? What's the sine of minus theta? Negative sine. So the sine of minus theta is negative sine theta. Oh, hey, cool. Does that tell you what the cosine of pi over 2 plus theta is? Yeah, it is negative sine theta. Cosine of pi over 2 plus theta is negative sine theta. That feel pretty okay? Cool. Do you think you could do something similar to figure out sine of pi over 2 plus theta? Sorry, I phrased that the wrong way. Do something similar. Figure out sine of pi over 2 plus theta. Once you have it written down and feel reasonably confident, we'll touch base. Multiple choice. Once you either have it walked out or feel like you have something worth saying, we'll come together. Well, on the other hand, how do people feel rather stuck, like they're not sure how to begin? Cool. So we'll follow a similar strategy. So in order to compute sine of pi over 2 plus theta, we'll think about sine of pi over 2 minus theta. So now I'll play the same game. I'll put this in a box. And so now I'll ignore the thing in the box. I'll just call it box for now. I see there sine of pi over 2 minus a thing. Does one of the formulas on the board tell you what sine of pi over 2 minus a thing should be? Yeah, what's sine of pi over 2 minus a thing? Cosine. It is cosine of that thing. And what the thing is matters. So it'll be cosine of box. And what's the thing in the box? Negative theta. All right, so now I have an easier problem, right? What's the cosine of negative theta the same as?
Negative cosine.
Careful.
Oh, negative cosine theta.
Careful.
Oh, yeah.
Just cosine theta, right?
Yeah.
Cool. So apparently the sine of pi over 2 minus theta is the same. Is the same as just cosine of theta. Now, I guess that made like the setup to do a multiple choice thing silly. Let's also try to approach this, right? Because that was a few algebraic steps. One could imagine a world in which something strange went wrong and maybe you screwed up a negative sign by doing one of the steps incorrectly. Let's try to draw a diagram of this and figure out whether it should be positive or should be negative. So, no, there's space here. Let's do a quick check by drawing a picture. So let's take a nice little angle in quadrant 1. There's an angle that sits in quadrant 1. Let's draw a picture of pi over 2 plus that angle. So that means I need to go forward by a right angle, because that's pi over 2, and then forward by that small bit. It is, in a slightly more formalized way. This a very similar diagram to this is on the next page, if we want to hit it. So, what quadrant does that orange angle live in? 2. So should cosine be positive or negative? Negative. Cool. Negative sign checks out. Should sine be positive or negative? Positive. It's in quadrant 2. So the lack of a negative sign checks out. People feel pretty good about that? Cool. So there's another much more geometric way to attack this particular problem, which we can do if people would like. I guess we need to do that like next row of what geometric functions do. Would you also like to see a more geometric picture of the same? Is there demand? Okay. I think I saw a few hands, so let's do it. So I think I will do it by studying some triangles. So that orange triangle is a right triangle. This horizontal side length, how long is it? Cosine theta, also a little bit less than 1, but more precisely cosine theta. What's the vertical side length of that triangle? Sine theta. All right, so if you like, that's the philosophy we used when we built the SOHCAHTOA rules. We started with that picture. So let's take exactly that triangle and rotate it 90 degrees about the origin. Then we'll get this new orange triangle. And all of the side lengths will be the same, just shifted. So now this length is cosine theta, and this length is sine theta. I think this is enough to determine what this point is in terms of just theta. So the y value is sine pi over 2 plus theta. But that's the same as how tall this triangle is. How tall is this triangle? In some sense, you're both right. It's cosine theta, and it's sine of pi over 2 plus theta. So these two things have to be the same because they're both height. So this triangle has height equal to cosine theta, but also height equal to the sine of pi over 2 plus theta. Oh, neat. So those two have to be the same. Sine of pi over 2 plus theta must be the same as cosine of theta. Let's also think about the horizontal distance. This horizontal distance is sine of theta. That should be the same as the x-coordinate, right? Except that it's pointing in the wrong direction. It's going to the left instead of the right, so it should be negative. So the width is sine theta, also known as negative cosine of pi over 2 plus theta, right, because it's going to the left. So the cosine of pi over 2 plus theta is negative sine theta. That seem pretty okay? Let's compute some things using this. I don't know. People feel like doing one of the secant, cosecant, tangent, cotangent computations? I think I want to do one in particular because it'll be interesting to do, and then we'll see something geometrically. Let's compute tangent altogether, and then I'll write down some things for the other ones. So the tangent of pi over 2 plus theta, let's try to compute that. Tangent pi over 2 plus theta. What is tangent in terms of sine and cosine? Sine over cosine. So I'll take sine over cosine at that angle. That is equal to the sine of pi over 2 plus theta divided by cosine pi over 2 plus theta. Oh, cool. Now I'm in the situation to use the first line. What's the sine of pi over 2 plus theta equal to? Just cosine theta? How about the denominator? Negative sine theta. So I know what to do with the negative sign in the denominator. I can just pull it out front. So this will be equal to negative something. It'll be equal to negative cosine over sine. Which trig function is cosine over sine? Yeah, cotangent. So tangent became negative cotangent. And maybe I'll point out why that seems interesting. So let's just think about these two lines. Maybe it's useful to have them both drawn at the same. So if you think about it for a second, the difference between those two angles should be a right angle, should be pi over 2. So what's like the fancy word for the way that those two lines intersect? They're perpendicular to each other. Do you know how the slope of a line that's perpendicular to another line should compare? It should be negative the reciprocal. Oh, cool. Cotangent is the reciprocal of tangent, and it's negative. So this is exactly what it had to be. So I'll just go ahead and write out the rest of the things in the table. I'll leave it for you to check at your leisure. Cotangent will become negative tangent theta. Cosecant, cosecant is 1 over sine. So it'll be 1 over, nope, what am I doing? Cosecant will become secant theta. Secant will become negative cosecant theta. That feel pretty okay? I suppose the one last thing to do in this note pack is we'll come now with this. We're doing this the wrong way. Fill in this. So cosine of pi over 2 minus theta became sine theta. Sine pi over 2 minus theta became cosine theta. Cosine pi over 2 plus theta became minus sine theta. Sine pi over 2 plus theta became cosine theta. That all feel pretty okay? Cool. So, I think here is what I'll encourage you to do, and I'll allow like 5 minutes for this, and then we'll see if I actually think people are using the time well. Those 15 things to compute are essentially homework problems, and they're kind of double-dipped homework problems. I think they're reflected in the web walk and then also in the open-ended part of this particular lecture. So, you have lots of people around you to talk with this about. Make a pass at computing these things. Depending if people are working well together, I'll allow more time for this. You might want to move if you want to walk with people. There we go. It's a slightly inconvenient day to not have a note pack today.
Yeah. Oh well.
It happens.
Yeah.
there's more stuff I want to do today, but people think that this particular set of problems now seems perfectly reasonable. If maybe you're allowed more than 5 minutes to do it all. How many people made it to the problems 10 through 13 range? How many people got to that point and felt stuck and didn't know how to proceed? Oh, cool. Excellent. Then I'm feeling pretty good. So, then I won't say anything more about this assignment now. You know my policy about the 5 to 10 minutes before class. Ask me anything then. So, let's carry on introducing. Yeah?
Just like to make sure that I'm doing this like right, it's like the sections of the problems 10, 11, 12, 13, do they still use that like cosine of alpha is 3/5? Is that still applied? Okay.
Same angle. Yep. Yeah, so maybe you all noticed that like amongst all of these problems, you really only see like 4 different numbers. There's going to be like a 3/5 showing up, a 4/5 showing up, and negative those two things showing up. Cool. So, yeah, these will be up amongst those same things. So let's talk about graphs of trigonometric functions. Now, on the one hand, like you've seen the graphs of the trig functions at some point because we pulled them up using a machine. Let's do exactly that again. This first bit is going to guide us through the computation of the graph of sine. So let's just go ahead and remember what the graph of sine of x looks like. Not sine of 9x. So let's even try to use the things we know to get some of the facts that appear on this graph. Well, I guess I can leave that up. Yeah, this will do. So let's start by plugging in some points. So I guess it's not there anymore. The numbers aren't up right now, but let's just remember the things we can remember. Let's see what values for sine you just already remember. What's the sine of 0? 0. Right, it should be that. Sine of pi over 6 is right here over 1/2. 2, 1, 2. Also known as 0.5, since we're going to try to sketch a graph. What's the sine of pi over 4? Root 2 over 2. And what is that about? 0.7. And we could get more digits than that, but since I'm going to draw something by hand, I'm not going to be able to draw better than the tenths anyway. Pi over 3. Root 3 over 2, which is about I mean, this isn't the type of thing that you should just like have off the top of your head. I was anticipating people taking out machines, but I could do that too. Square root of 3 over 2 is oops. Is about, that rounds up to 0.9, right? And let's also think about pi over 2. What are the trig functions at pi over 2? What is sine of pi over 2? Decimal approximations, 1 is 1. Gesundheit. So let's plot those points at least. That'll give us something. Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is about 0.7. So let's see, there's 0.5, 0.6, 0.7. Sine of pi over 3 is 0.9. Sine of pi is 1. So there's something anyway. we can fill out the rest of this table too, right? As you go around the circle, you're going to see the exact same values going back down until you get to pi. So you know the remaining entries. Sine of 2 pi over 3 should be the same as sine of pi over 3, should be root 2, root 3 over 2, also known as 0.9. I guess I should indicate that these are the ones that are approximate. 1/2 is exactly 0.5. Root 2 over 2, 1 over 2, 0. So let's plot those also. So then it starts coming back down, right? So with that as a starting point, let's just interpolate between these. Doing my best to do so reasonably smoothly. We see a graph that looks something like that. People feel pretty good about that? And that graph even seems reasonable. Right? The y values go up until you make it to a right angle, then they come back down. All right. So we also have another property. If we add pi to an angle, sine becomes negative. Sine of pi plus theta is the same as the sine of theta. So that means if we increase all of the angles by pi, then the output becomes negative. Well, here are all of those same inputs, but pi added to them. The outputs are the same as these, but negative. So there's the graph of sine of theta between 0 and 2 pi. There's another useful fact here in this list of facts. If we add 2 pi to an angle, we get the exact same sign back. So that means I should be able to take that orange thing and shift it left or right by 2 pi, and that's still the graph of sine. So let's do that. I'll copy this down here. I should be able to shift that left or right by 2 pi and get the exact same graph back. So there's shifted right by 2 pi. Here it is shifted left by 2 pi. Cool. That feel pretty all right? So here's something to notice. This function just repeats. Its graph just follows the same pattern over and over again. A function of that type is called periodic. The period is how long you have to go until it repeats again. So this function's sine is periodic. Its period is 2 pi. Cool. Folks with me so far? Nice. Let's read some things off from this graph. Right? Once you have a graph, you can read all kinds of stuff from it. What's the maximum value sine takes? 1. And I guess that makes sense from the point of view of the unit circle also. The sine is the y value on the unit circle. What's the biggest y value you see on the circle of radius 1? 1. The y values never go over that. From this, we can even see what inputs result in that output of 1. So I see that place where the output is 1. What's the input that corresponds to that?
Negative 1. 0.
Also not 0. I hear a pi over 2. You're good. Hold on to that number 0 once we talk about cosine. So what inputs result in it? So the, maximum value is 1. What inputs achieve it? Pi over 2 does. Do you see any other inputs in this picture that also result in that same output? Yeah, what input do you see?
Yeah,
5 pi over 2, and maybe I'll unsimplify what you did to make it clearer how it came from. That's 2 pi plus pi over 2. That's how you got it. Which is the same thing as 5 pi over 2 So you could also take pi over 2 and add 2 pi to it. And I think I'm going to give myself lots of space, because I'm going to add some decorations. Could I also go left by 2 pi? So I could subtract that also. Could I go right by like 10 times 2 pi and also see that same maximum? Yeah, it's not on the amount that I drew, but that's because I only had so much space. So I could shift by any multiple of 2 pi and still have an input that produces a maximum. Cool. That feel pretty good? What's the minimum value? What is one input that results in that minimum?
3 pi over 2.
How many people would sooner have said negative pi over 2? I mean, you're both right. Because negative pi over 2 is 3 pi over 2, but then shifted left by 2 pi. There are all of the x values that produce the maximum. And notice, you would be just as right if you said x equal to negative pi over 2 plus 2 pi k. And that's something that's just generally true about periodic functions. Once you see something happening once, it's going to happen over and over again with regularity. And once you, depending on which first time you see it happening, the way that you write down all of them might look different. But they'll all look different by a multiple of 2 pi. Does that feel pretty okay? Cool. Is sine even or odd? Odd. Either because of this rule, or because apparently I could fix the origin, spin it 180 degrees, and get the same graph back. Could we figure out where sine is increasing? Yeah, and let's do it using, I guess, this color coding strategy. At the origin, at 0, does it seem to be increasing or decreasing? Increasing. How far to the right can I go with it's still increasing? Up to like there, I guess. So up to pi over 2. So that means pi over 2 is the right endpoint of an interval of increase. How far to the left could I go? Negative pi over 2. Oh, so I guess that means that at pi over 2, it switches to decreasing, right? After pi over 2, how far does it go before it stops decreasing? Right here at 3 pi over 2? So from pi over 2 to 3 pi over 2, it decreases. So I guess that means at 3 pi over 2, it starts increasing again. How far does it keep on increasing, starting at 3 pi over 2? I hear a 5 pi over 2, and I think I also saw a 5 pi over 2 lip synced? Mouthed?